Yeah, sometimes it's more.
So it's comparable to the number of people who were given versus.
Yeah, that's right.
Okay, everybody, thanks for coming to the PH lecture this year. So I'm delighted to just give you a little bit of background about the PH lecture and also introduce our PH lecturer, Morgan MacLeod. So the PH lecture is an endowed lectureship, and it was established by the Hertelendy family of California. And Dr. Hertelendy is an alumni member of the Smithsonian National Board, and for several years he served as an official liaison to SAO. The family established this lecture to encourage and celebrate the observatory's outstanding young scientists. So I'm delighted to introduce this year's PH lecturer, Morgan MacLeod. So Morgan got his PhD at the University of California, Santa Cruz, and he was working with Enrico Ramirez Ruiz. And he's now a Clay Fellow in SSP and also the ITC divisions. Of relevance to this lecture, he grew up next to the ocean on Oars Island in Maine, watching waves break, and he's still talking about the waves. Just
Haven't gotten over it.
Different types of waves now. And he's been fascinated with astronomy since a sixth grade class trip to the planetarium. It would have been a really excellent planetarium trip, I think. During his talk, he'll tell us about breaking waves on a star. Before starting his Clay Fellowship, Morgan was an Einstein Fellow and an ITC Fellow at the CFA, as well as a postdoctoral member of the Institute for Advanced Study. And I'm really looking forward to hearing about breaking waves on a stellar shore. So thank you, Morgan.
Thank you. And that's such a
joy to be here, and thank you all for coming. I think, let me lower the lights. Thank you, Sean. Well, it's such a joy to be here and be able to share this work with you, and I think as a reflection on the fact that this is a lecture for an early career researcher, I think it reflects the sort of science I've gotten the chance to do here at the CFA, the community that I've had, the mentorship that I've had. And so, I view this as much a celebration of that scientific environment as anything else. And so I'm extremely grateful. Along those lines, I want to start with this beautiful image that Melissa Weiss made this summer when the work I'm going to tell you about today was being published. And this is up on the CFA homepage right now. Maybe you've seen it there. It's one of the news items that scrolls through. And so we'll come back and we'll talk about what's going on here. But first of all, I want to talk about stars in pairs. And of course, our sun is a single star. We know that very intimately. But then many stars are in pairs, and sometimes in pairs orbited by planets. And of course, this is an artist's conception, but we have data as well. So this is Chara interferometer data of algal A and B, and they have, of course, a 2.7 day, 2.68, I think, day orbital period. Here you can see them going around each other. I think this is just remarkable. But we've seen examples of this in a lot of different situations, and something that we're learning as people have synthesized that information is that stellar multiplicity is not just sort of this special exotic circumstance, but it's actually extremely common. And it depends on the mass of the stars involved. So down around 1 or even 0.1 per times the solar mass, less than half of stars are in binary or higher order multiple systems. Up near 10 solar masses, actually the majority of stars are in either pairs or triples or more. And so something that I think this is teaching us is that the interactions and the sort of at least more complex and more varied stellar lifetimes that encompasses are actually part of sort of the core story of how especially some of these more massive stars live their lives. Speaking of how stars live their lives, we know how stellar evolution works in the sense that it's fueled by this burning reaction. We're taking hydrogen, we're turning it into helium in the stellar cores, and the stars are representation of that hydrostatic balance. And we also know that as that goes on, stars burn more and more vigorously and their outer layers puff up. And this change in size is really dramatic, right? So the sun will expand by a factor of a few hundred from its current radius. And that means that many of these systems that we see as separate pairs now, in the future, can actually directly interact. Mass can stream from one star to another. So here's that plot, again, reposed, but as a close binary fraction, where close here is a relative term. It means less than 10 AU. But very roughly, this is the fraction as a function of primary mass of those stars that will directly interact in the sense of either stream mass from one to the other, potentially merge or do other things. So again, this is 15 or so % at a solar mass. But as you go up to 10 solar masses, it's actually more than half of stars are in these close binary systems. Will there be affected at least tidally and maybe even more directly by each other? For another kind of concrete but scaled down a little bit example, here's kind of the host of exoplanets that we know right now in units of their semi-major axis and planet radius. And as their host stars evolve, they'll get bigger and bigger and bigger. And what happens is that all of these planets that are within a few hundred stellar radii right now will eventually be swallowed by their host stars. And so this whole exoplanet population that we're discovering is kind of subject to that future interaction, as of course is our inner solar system. Something that I think is incredibly fortunate is we think we caught this process in the act, and this is, when I say we, this is a huge team of people, including a number of people at the CFA, and led by my colleague Kishali Day. And what we saw was the brightening and kind of dusty infrared aftermath of a star that essentially brightened and then faded back towards normal, and along the way sort of burped out a lot of dust. And we think that represented the engulfment of a giant planet by that host star. So in the sense that all these interactions happen, many of them probably aren't completely gentle either. You can imagine you take two stars and they come together. That's not necessarily a completely gentle process. And along the way, there's light that we can see and sort of traces left on those stars. Okay, so swallowing a planet maybe is one thing. We can imagine the star continuing about its business, but what if there's a star in the way? And that's what I want to focus on today. And in particular, we talked about this huge fraction of stars in multiple systems. They have a wide range of initial eccentricities, orbits, and that's part of why their evolutions have been so complicated to piece together, because there's this incredible branching of possibilities once you have not just one star, and everything seems to be kind of controlled by its mass and metallicity, but you have the different orbits, the different mass ratios, the different sort of evolutionary states. But if we zoom in on one aspect of that, these systems seem to have a broad eccentricity distribution, which means that there's lots of eccentric systems for every circular one. And as they start out, they're essentially separate objects. So they're not necessarily rotating synchronously with one another, that sort of thing. But as they grow bigger and bigger, you can imagine the Earth growing in the Earth-Moon system. That would be strange, but let's imagine it for a second. The strength of the tides that Earth would experience would get stronger and stronger because it would be filling up more of the space between the Earth and the Moon. And so some of the question here is whether the dissipation that's associated with tides acts to kind of damp out that eccentricity and lock these systems together before they start to exchange material, or whether there's like a runaway sort of growth and these orbits stay eccentric. And in particular, I think it depends on a ratio of timescales. So one timescale is the time over which the star is growing. It's getting bigger, it's kind of filling up the space of the orbit. And the other timescale is the tidal dissipation timescale. Of course, this is the more complicated of the two. We think we know how sort of stellar evolution burns through fuel and modifies the star's radius. What happens with the tides is a little more complicated. But basically, there's two situations. One is that tides act faster. We think that situation corresponds to when these stars have a vigorously convective envelope. So that tends to be low-mass stars or giant branch stars. And in those cases, what happens is you have this coherent shape of the tide. It has these two bulges, right? And then you have all the messiness of convection. And you take that coherent shape and you essentially dot it with that random velocity field, and there's just dissipation associated with the coherent velocity field and the randomness. And so dissipation in these cases is comparatively, and comparatively I mean to the other category I'm going to talk about here on the right, efficient. And what that means is you often end up with situations where a pair is tidally locked, and that means, it rotates with the same frequency as it orbits. Think like the Moon relative to Earth. Earth is not tidally locked. We spin in 24 hours. The Moon orbits in 28 days. But the moon is tidally locked relative to us, right? We always see the same side. So then you get this damped evolution. A completely different possibility is if the radius growth is faster, this can happen in massive stars where stellar evolution is just happening faster. It can also happen in stars that tend to have radiative envelopes, like Hertzsprung gap stars, where the tidal dissipation itself is thought to be less efficient. In this case, rather than damping out into those equilibrium configurations, you stay out of equilibrium as stellar evolution proceeds, and you go to kind of stronger and stronger and stronger out of equilibrium tides. We have one glimpse of this process in action through these stars, which I think this plot is kind of delightful just because it's like such a range of possibilities. But these stars became known as the heartbeat stars, and they were theoretically predicted before they were discovered in the Kepler data. And what's going on here is we're looking at eccentric binary pairs that are stretched and distorted every periapse passage. And when we look at the stretched out larger surface area side of a given star, it looks brighter. And when we look at the narrow kind of nose end, it looks dimmer. And we see a big pulse once per orbital cycle, once per periapse passage in these eccentric systems. And then they fly away and go about their business, and then they come back and do it again. So that's these big pulses. And then there's a bunch of little wiggles in between. And the wiggles are where these stars have flown by each other, and they're essentially set ringing. And as they fly away, they're removed from that forcing of the periastron passage, and they're just free oscillating around their own equilibrium shape. So that's what all this is. And then the fact that they became heartbeat stars, I mean, maybe the pulsing is kind of like a heartbeat, but really it's that these plots, these light curves, just look a lot like a Hertzsprung, what's it called? An EKG, not a Hertzsprung-Russell diagram. It's like whatever it is for the body to have a Hertzsprung-Russell diagram. Okay, an EKG, where you get a pulse of a heartbeat and then some time between. So Kepler, in surveying roughly sun-like stars, was looking, as it turns out in hindsight, at kind of this case where tides were relatively efficient, and we're looking at situations where these systems are essentially actively damping and in progress towards kind of this equilibrium configuration where they're tidally locked, and maybe you have that classic picture in your head of Roche lobe overflow and a thin stream of material from one star to another. I use the word in action in the title of this particular slide because I think here we're seeing not a pair of stars that's subject to future interaction or a system that is already damped out and is in its equilibrium configuration, but one that's kind of on the way. And so maybe it's really interesting to study this tidal dissipation process as it's happening. Okay, the last thing I want to point out here is the amplitudes. So the y-axis here is in parts per million, but there's thousands of parts per million, so these are order of 1 part per thousand. 0.1% variations in brightness. And actually a pretty good estimate for what that means in terms of the distortion of the star is that it's a 0.1% distortion in the stellar shape, basically. We see it side on, it's 0.1% brighter. We see it edge on, and it's 0.1% dimmer. Okay, so that's a big tide compared to the Earth-Moon tides, which are 1 meter on 6,000 kilometers, factor of 1,000 larger, but it's a factor of 1,000 smaller, kind of than an order unity tide. Recently, some objects have been identified as heartbeat stars that were known to be variable for a long time, but we didn't actually realize they were heartbeat systems. And this is one of them. It's called Macho 80.7443.1718. And I got really good at cutting and pasting that as I wrote about this object. But what I think is amazing about this is essentially the normalization of the y-axis on this light curve plot. So where these systems, before I was showing you a sort of part per thousand variation, this is all of a sudden a 20%, plus or minus 20% swing in brightness. If that's related to the amplitude of the distortion of this object, all of a sudden we're looking at a much bigger distortion, kind of like a 10 or 20% distortion of the surface area that's projected towards us. Through some amazing follow-up work, people identified the orbit of this system, the masses of the components involved. We don't exactly know the inclination, but it's something like a 35 solar mass primary star and a maybe 10 to 15 or 16 solar mass secondary. So this is a massive but unequal pair, and they're in an eccentric orbit with an eccentricity similar to 0.6. Okay, and here now we're zooming in on the phases of that sort of big swing in brightness and then increase, and a couple things are happening. First of all, the amplitude of this swing is huge. Second of all, as the star leaves this sort of region of the periastron passage where that distortion is most extreme, as they start to fly away, there are signs of that huge tide, that distortion kind of collapsing on itself and the star kind of ringing. And what I see here, and these are test data, and that's why you have kind of this really complete and extreme phase coverage, is that these points don't really necessarily overlap. And so it's not completely systematic how this tide is collapsing each orbit. And if you look at the just sort of continuous light curve rather than phased on top of itself, what you see is that, these little wiggles are a little bit different each time. So we have this sort of collapse from this distorted equilibrium distortion at periastron passage to the ringing oscillation. The spectra of this source are also pretty amazing. So just at the moment of periastron passage, we see a very narrow absorption line in the Balmer series. This is H beta. And at other phases, you see this combination of emission and absorption with this very broad emission component. But that emission line disappears at periastron passage and then reappears again, and its violet to red ratios change over time. Andrea took some of these spectra one night at Magellan, I think. And when you were observing on somebody else's program, you're one of the authors of this paper, whether you know it or not. So that's really, probably they interrupted your observation and you wanted to be doing something else. But the other thing I think is worth pointing out is the name of this object has a Macho identifier name because it was first identified as a variable star in the Macho survey. And here's the long-term light curve of the source, which isn't particularly illuminating until you zoom in on different periods. But back in the early 1990s, it was doing the same thing that it's doing right now. And so where TESS gives us this precision window into its behavior, it's actually really interesting to see that this system and the top axis is sort of number of orbits. This has about a 1 month orbital period. Has been going around and these kind of really extreme wave has been raised on it over the course of hundreds of orbits. So on some level, when I first saw this, I thought, wow, isn't that a really kind of unstable or like quickly decaying or just sort of like especially violent moment in this star's history, but clearly it's been sustained for quite some time. at least in sort of our in our time units. The other thing that's I think that baseline has given us access to, and this is an O minus C diagram, but what it shows is that the orbital period is changing over time. And it's actually decaying by about 1 second per orbit, or about 11 seconds per year. And that means that there's an offset of about a quarter day between when this time series started and now. So a lot of the work that I do is making gas dynamics models of systems like this. And I think it comes from the impulse that, you know, if you're a chemist, you have a lab and you get to ask a question and see what happens. And, you know, here we're not at liberty to do that in most of astrophysics because we have to just watch and wait and see what we see. But if we want to do an experiment, the next best thing we can do is a computer model. And so this comes from sort of an impulse not to perfectly reproduce the data, but to try to understand some of the physics that's going on. And so here I'm going to show you models, in terms of not perfectly reproducing things, where the secondary star is a point mass, and we're just modeling its gravitational interaction with some gas that represents the stellar envelope. So this is gas in hydrostatic equilibrium around another point mass. And if I start out a system that is tidally locked, so in this configuration where it's synchronously rotating, and here this image is also synchronously rotating. So we're looking down through a slice in the orbital plane, but that is co-rotating with this system. And we're looking at gas density in units of the average density of the star. And what you can see is that the fluid that's in the stellar, in this rotating frame, because it's rotating synchronously, doesn't experience a time-varying tidal potential. It's just, at the beginning here, it's just kind of stretched out, and then it forms this thin stream, and it streams over to the other star. This particular situation was unstable in the sense that once this mass transfer started, it ramps up and up and up and up, and you end up in a very dynamic situation at the end. But at the beginning here, this is kind of the outcome of that tidally damped evolution, where you arrive at a circular synchronous orbit. And then eventually maybe this system keeps evolving and it goes into a mass transferring phase, and that mass transfer might be unstable, that's what's being modeled here, but it might also be stable. Now, the situation that we have is a little bit different. So this star is experiencing these tides, but only once per orbit in this really eccentric situation. And so let me walk you through these panels and then we'll see what happens, basically. So here's the second mass. Here's that gaseous envelope. And this is essentially the same picture we were just looking at, a slice of density through the plane of the orbit. This is the gas entropy in that same slice. And then that map up there is the radial velocity on the surface of this spherical star. Okay, so the little perturber flew by, and then it raises this tide, but you see this really dynamic wave instead of kind of that perfect teardrop shape. And the reason is because the gas isn't just going along synchronized with the orbit. And what we see instead is that you get this wave that's raised, and then these caustics form, and those are actually shocks in the gas. And there are shocks that race through this material, and it raises the entropy of some of the gas and creates this kind of circumstellar envelope of gas. And along the way, if you look at the radial velocity on the surface, there's this quadrupole pattern, and it's getting weaker in time. So it's actually damping out as those shocks dissipate into this circumstellar atmosphere. But at the root of what's going on here is that what starts out in those first frames as this kind of smooth wave-like disturbance turns into a big mess. And I think we can see an analogy for that when we look at breaking waves on a beach, for example. So what's happening in a shallow water breaking wave is that as it approaches the shore, the top of the wave moves faster than the bottom. And so the top of the wave gets kind of progressively ahead of itself, and the wave steepens, and at a certain point it just falls over, right? Because the top of the wave gets ahead of the bottom of the wave. Here, something really kind of parallel is happening in that in this passage, the wave gets out of sync with itself, and if that loss of coherence is supersonic, above the sound speed of the gas, then when it falls back on itself, that will form shocks, and this kind of irreversible change in the in the fluid state, rather than kind of just a smooth pressure wave. Okay. So that was a sort of idealized situation where I just sent a companion by on a single passage. It was in a parabolic sort of orbit. I just wanted to see what happened over one passage. And it seems like these tides that you raise, at least in some cases, can break like a breaking wave. But then the question of what might be going on in this system still remained, and in particular, how that might proceed over many orbits, and how can that kind of extreme tide persist over many orbits was still in my mind. And so here's that primary star, here's the secondary star, and what you see is that every time it goes by, it both kind of strips material from this extended atmosphere, and it's got a cloud of gas around it as a result, but also it raises a new tide on that star and relaunches these waves that are kind of racing around and seeding this atmosphere. So the fact that they're not in sync as they go by each other, and you can imagine that they essentially can't ever be in an eccentric orbit. You will always experience time-varying tides in an eccentric orbit as you come closer and then further away. And what that means is that we're going to see the second star fly in from the side. And here the brightness is representing the flux, and the orientation is that we see on the sky. That basically, as the distortion of that tide collapses back to the stellar surface, it seeds this kind of turbulent layer in the equator and drives essentially dissipation, which is taking energy from that orbital motion and depositing it onto the stellar surface. So in my title, when I said breaking waves on a stellar shore, really, of course, that means on the stellar surface, and is the location of this dissipation. And of course, the surface of a star isn't a really well-defined thing, but what's interesting here is that this is happening in the very outermost layers of the star, and it's actually forming this bifurcated structure where you have the bulk interior of the star and then a high entropy layer that's been shock heated by this interaction once per orbit. So we can take that simulation, and I was showing you essentially a slice through the hydrodynamic simulation volume that represents the photosphere, and then the fluid blobs, depending on their sort of orientation. So you see the limb darkening there, and since we know the angle of this object on the sky, we can actually then propagate that light to ourselves. So here's the flux and the line of sight velocity. And what you can see is that the simulation isn't perfect, but it captures some aspects of the variation. One of them is that this is a pretty large amplitude variation. And actually, even in the simulation, I don't quite match the photometric variation that we really see. There's maybe another factor of 50%. So this star is really having something quite dramatic going on. And then in between, these are kind of the free oscillations. The exact mode that gets excited is usually based on a resonance condition. So in this object, if you look in the 1990s MACHO data, it's the 25th harmonic of the orbital period has the highest spectral density in a Fourier series. But in the test data, it's essentially equally weighted between the 24th and 25th harmonic. So there's some thought that with that sort of cumulative change in the orbital period, you might be changing the resonance condition a little bit between a couple modes. All of that to say, the fact that the simulation didn't necessarily match the modes that are excited in the tidally driven free oscillations is maybe not surprising, since that's kind of a chaotic or resonant behavior. The other thing that we see is, there's some imprint of those oscillations in essentially these like wiggles on top of the radial velocity curve. So this smooth dashed curve is essentially like the point mass radial velocities, and then the wiggly curve is when you add essentially this tidal pulsation on top. Okay, so I'm zooming in here at the periastron passage. At the point of minimum brightness, as we look at this system, the primary star is me, and then the secondary star is behind us, essentially. So we're looking at the secondary star either crossing behind or maybe not being eclipsed. We can't quite tell, depending on the inclination. And then at the brightest point, we're looking at the star face on, and then as we sort of proceed, we're watching the wave break actually in this quadrant of the star that's facing towards us. And if I zoom in a little bit, maybe you saw kind of that there was this stuff going on outside the star. Here we're flying along with the primary star. You can see that every once in a while, the secondary kind of comes along and stirs things up as far as the fluid within the star is concerned. And that stirring up is kind of dramatic in that it launches these waves that persist through to the next periastron passage. So in this still frame at the end, you can see that actually there's this interface here, and there's a shear layer here, and there's all these kind of spiral shock waves that are propagating out. And the action of all these shock waves is to drive dissipation. So it's taking energy from, originally from the orbit, giving it to an oscillation, and then damping it out into heat in these outer layers. And along the way, if we zoom in, you really have to zoom in. But if you zoom in, right kind of here, at the edge of this tide, what we see is that it sort of buckles on itself. And in red here, we're highlighting areas of strong flow convergence. And that's where kind of these shocks are seated. Now, the breaking ocean wave kind of steepens, gets ahead of itself, and then falls over. But here, this fluid is conserving angular momentum. So as it moves out, it rotates slower, and the wave kind of folds over on itself backwards. So the crests, in this case, are actually moving slower than the trough of the wave, and the sort of fallback is happening kind of in the reverse direction of a breaking ocean wave. Now, this is a slice through the star at apoapse, at the sort of furthest point between the two stars. And we're looking at the angular velocity of material in the interior. And it started out uniformly rotating in my particular model, not because that's truth, but because that was sort of a simple initial condition. And what's happening is we're seeing this wave here. This is a relatively high order, what's called a G mode oscillation, where a lot of the displacement is horizontal. And there are nodes of it as you go in, so like 1, 2, 3, 4, 5, and then if you look, there are more as you go in. So here's the velocity over the average velocity of the envelope. So it started out all kind of uniform, and now there's this wave pattern on top of it. And so what it seems like is happening, if I follow back through the simulation, is that on the near side of the star to the secondary, where that wave collapsed on itself, it launches this disturbance that then propagates around. And this is actually, mostly we think of tides as being symmetric, but this is an L of 1 disturbance. So it has one node in angle, in azimuth, and many nodes in the radial direction. And actually, as it's dissipating, you can see something here in the averaged angular velocity, which is that the dissipation of these tides is actually increasing the angular frequency of the outer layers of this star. It's depositing, the dissipation is depositing angular momentum and helping spin this star up. The other thing that breaking wave does is, here we're just looping the periastron passage, and I'm showing you something like the photosphere in blue, and then in yellow, lower density material just outside the photosphere. And that is, we don't have the thermodynamics of that optically thin material particularly well in the gas dynamics simulation. So I can't make a synthetic spectrum for you, but we can look at its dynamics. And what you see is that every periastron passage, a lot of that atmosphere is being stripped, but then as the wave breaks, there are shocks and is reforming that kind of hot rotating circumstellar material. And if we look at the emission line profiles, again, of H beta as a function of phase, you can see that they're really time varying. They're also broad. The breadth represents the rotational velocity, and I think the time varying aspect is essentially the stripping and then reformation of this shock-heated atmosphere once per orbit. If we look at the changing V to R ratios, just in a couple snapshots through the periastron, so essentially just before, approximately at, and then just after the periastron passage, what you can see is there are these wings here of first red material, and then it kind of narrows where the star is like all perfectly lined up along the line of sight. And then it broadens again where the secondary is kind of winging material off to one side. And so you go from there being a red tail to a narrow line to a blue tail as a function of time. So I think the thing that I want to emphasize here is that you can see my really high-tech simulation of this process, that this is a star where we're seeing a tide that has gotten really nonlinear. And nonlinear in the sense that rather than just being kind of a smooth, continuous wave, it's getting in its own way and crashing and doing all this messy stuff. And every periastron passage, there's this strong distortion of the star. It collapses on itself. It shock heats. That wave breaking happens just as the star is kind of freed from the tidal force of its companion, and then it goes about its ringing. And then as it goes around the orbit, there's dissipation. It seems like in our simulations that dissipation is doing a couple things. One is that it spins up the surface of that model star. The second is that that dissipation is happening kind of localized on the surface. It's not damping into the deep interior. And I think that means a couple things. One is that the shape of this star, and we can tell this from the rotational broadening of the lines, it's rotating actually, as far as we can tell, at breakup. And at breakup angular velocity, this star is incredibly oblate. So its equators are 50% wider than its poles. And we don't know, how deep that angular velocity persists. It could be just the surface layers that are rotating this fast. But it's the deposition of angular momentum into those outer layers from these shocks that seems to be responsible for that. And it gets even weirder in that breakup angular velocity is faster than the periastron angular velocity, in that if this were sort of a weak tidal dissipation process, you would expect a slower rotation. But it seems that this like shock-driven tidal dissipation is trending you towards a higher angular velocity. The second thing is that imagine you put the heat deep in the interior of the star. It takes a long time for heat to get out of the center of the sun. I think it's like 10 to the 5 years for a photon to like work its way out. So if we put the heat there, the star would keep going about its business, but it would also puff up in response to that heat. The tides would get even stronger. The energy deposition would happen even faster, and you'd just be in a runaway kind of guaranteed merger. But when we put it on the surface, it's actually free to radiate away. And we're seeing that radiation in those emission lines. And so if you add up the equivalent width of those emission lines, you get about 100 solar luminosities. And if you compare that to the 11 seconds per year, the power that would need to be radiated for that 11 seconds per year orbital decay rate, that's almost the same, to within a factor of 2. And so I think when we're looking at the emission lines and we're looking at that shock-heated atmosphere, we're seeing kind of the location of the dissipation of this tide. One aspect of that is that it's kind of leaving the rest of the star alone, right? The deep interior is kind of fine. And so if we think about, for example, the model where hot Jupiters are scattered towards their stars in eccentric orbits, tides are raised on them. They would need to damp those tides and circularize in these really small orbits. A really troubling thing has been that the amount, because of the mass ratio, the amount of energy you would need to get rid of in that process is way more than the binding energy of the hot Jupiter. But maybe it can survive a process like that if the mode of dissipation is such that it puts it only on the surface and it's sort of shining away continuously rather than being deposited in the deep interior. So there's lots more still to tell, but I think what's exciting is that in this system we're watching it happen. And when we watch it happen, we can move from the realm of sort of my simulation and my other computer simulation to actually comparing to the data and seeing what we can learn. And I think that's really exciting. So with that in mind, what happens next for this star? So I talked about a couple regimes. One was where the damping was faster than the stellar evolution. The other was the other way around. In this case, this is a massive star. Its radius is growing actually pretty quickly. And if we look at the current rate of damping, it's happening more slowly than the radius is growing. I think that's what got us into this situation where the tide is really extreme compared to the Kepler systems, which have these really small amplitudes that damp out. And that means that where we are now is this situation with these really extreme dynamical tides. And I think where we're going next is that these essentially continue up to the point of merger, where right now we're stripping a little material from the atmosphere every periastron passage. Probably next that will intensify until there's more and more material involved in this eccentric mass transfer. I think the most likely outcome of that sort of story is that eventually these merge into a single star. It has a helium core already, so that will persist in this combined star. It will be more massive, but some material will be thrown out. And along the way, you'll see both an optical and infrared transient. And I think as this continues to evolve, this is then a massive star with 3 to 4 solar masses of circumstellar material. And when we talk about supernovae with circumstellar interaction, maybe this is the sort of interaction that sets the stage for that. And then I think as kind of remarkable and bizarre of a situation as this is, and that's what got me sort of going down this path, the more I've studied this, I've eventually, I think, come to realize that this might kind of be a natural part of the story of an evolving stellar massive star pair, where tides basically aren't efficient enough to maintain those small amplitudes of the Kepler stars and damp them into these equilibrium configurations. You get these really dynamical situations instead. So I owe a huge thank you to Mercedes, but also Peter Edmonds, Megan Watzke, and Melissa Weiss, who did this art, for helping me when this work came out this summer. I got to talk to a lot of people, reporters, about sort of breaking waves on stars. They came up with great titles like, surfing on a stellar surface. People were asking me, like, could you make a plasma surfboard? And I was like, oh boy, I didn't think about that. Like in this sort of context, I can anticipate some of the questions that you all will ask me, because you work on a project for years, and along the way you think of a lot of things. But this was just a joy, basically. And I think through their help, we were able to get the word out about some really kind of delightful science that's happening here at the CFA. Okay. So I called this a heartbreak star, and now I'm going to look for more heartbreak. We have a program at Magellan in this current semester. See, the LMC is right here, so I'm saying it should turn around and look at it. And we're going to look for other sources with similarly large amplitudes. So I'll spare you some of the details of that, other than to say that by looking at the orbit of a given system and comparing the speed of the wave that's raised to the surface sound speed, which we can estimate from the star's effective temperature and colors, then we can say what might be the amplitude of a wave that would break, that would cause a shock rather than just a sound wave. And I've been calling that, in my head at least, a critical amplitude for these breaking waves. And then we can compare the distribution of sources that have been observed in the LMC in this particular plot, their amplitudes on the y-axis and magnitudes compared to the critical amplitude. So there's a little convergence factor between magnitudes and the physical distortion, which depends on the type of the star, and we don't exactly know. And there's other sort of factors that depend on the exact rotation profile that we don't exactly know. But if we sort of take those uncertainties at face value, we see that there's a distribution of, in blue, of main sequence stars, in orange of red giant stars. The red giant stars seem to cluster towards lower amplitudes relative to the critical amplitude. It's probably because they have stronger dissipation in their convective envelopes. But some of these main sequence stars actually approach this threshold. And I think threshold is the right word, because once it breaks, a wave doesn't get any taller, right, as it approaches the beach. That's a saturation of its height. And I think it's not by chance that the system that we were just talking about in these kind of units stands out a little bit. So I think the question to come is whether there will be more of these systems or whether we are kind of looking at a special object. But my thought is that if we go ever so slightly down in amplitude, and so this fall we're looking at the next 3 highest amplitude sources, we can learn things about where the threshold for a breaking wave is and how that kind of transition between an organized kind of linear wave of a tide and this completely disordered motion works. So with that, thank you so much for your attention, but most of all, I want to close with the idea that, these interactions between stars are, it turns out, not unusual, and they lead to these kind of rich phenomena in the night sky, from transients to extreme tides, but along the way, those are kind of transformative moments. So this particular star is spun up, it has breaking waves on its surface. Maybe it'll merge eventually. And I think if the more we can watch that process happen, we can learn about how the physics of how it works and how it transforms that large fraction of stars that live their lives this way. So thank you all.
So thank you, Morgan, for that excellent talk, and time for questions. Yes, Ramesh.
Nice work, Morgan.
Thank
Very
you.
interesting. Nice physics. I had a couple of questions. One, I mean, these are hydro simulations,
Yeah.
and you showed light curves. So how straightforward is it to go from the hydro results to actual, the brightness of the surface?
Yeah,
Right?
it's not straightforward. And I can tell you what I did, and you'll see how not straightforward it is. I think you can probably anticipate, but for everyone,
I couldn't figure it out.
basically what you have, the actually hardest part of these calculations is keeping the star in hydrostatic equilibrium on this hydrodynamic mesh. And so you're relying on canceling gravity in one direction, a pressure gradient in the other. And that means you have to resolve the pressure gradient, which gets smaller and smaller and smaller the closer you go to the stellar surface. And so if you want to resolve the photosphere layer, you need to resolve the pressure gradient at that photosphere layer. And I can get to within a factor of 10 of that gradient, but not to it. And so then from the layer that I have to kind of extrapolate the thermodynamics that I don't know. And what I did in this case is I just took a surface of constant density, and I said that its flux coming out of it would be proportional to its displacement from its equilibrium surface. So that's like a von Zeppel's law or something like that. The flux is proportional to the surface gravity, the inverse of the surface gravity. And I basically varied that prescription a lot, and it changes the light curve some, and it would change the light curve a lot more if the colors of the star were redder. But because you're in such extreme Rayleigh-Jean's tail in this particular case, you get kind of lucky. So I think there's a lot of work to be done in trying to treat kind of the radiative cooling of those overlying layers and then the thermodynamics between the stellar interior and the surface a lot better. And that's yet to come. I think it will be challenging, but probably there's something to be done that's a step above this extremely simple kind of take and below the real system's complexity. But I think that's probably where we have to go if we want to understand not just the order of magnitude level fluctuations. Yeah.
I had a second question, if Lisa will.
There were 4 other people with hands up, so we'll go to them first, and then we'll come back to you. We had some other questions. Yes.
It was kind of surprising that the resonance was such a high harmonic. You mentioned 25th. What the term is?
Yeah.
Can you repeat the question?
So it's kind of surprising that in the real system, the mode that appears in those free oscillations is something like the 24th or 25th harmonic of the orbital frequency. I think that's essentially a function of the eccentricity of the orbit. Because it's a high eccentricity orbit, that's close to the ratio of the natural frequency of the star compared to the orbital frequency. So if you ask what 1 over the dynamical time of the star is, that's kind of a characteristic time for a mode to oscillate. So there's time for a lot of oscillations before the next periastron passage. That's what that tells us.
Okay, we had Josh, and then I think there was another question back there.
Morgan, lovely talk. But did you follow how much mass is being lost on each periastron passage? Because I don't understand why these systems don't circularize on shorter timescales, and then that we don't see these for very long.
Yeah.
So has that been taken into account?
Well, in the sense that basically, I think right now what's happening is an extremely small amount of mass from that atmosphere layer is being transferred. And it's so small that you wouldn't see any accretion luminosity, anything like that. And it actually isn't enough to drive this towards a circular orbit. So it's maintaining its eccentricity. And in the future, as the star grows, say 10% more, there will be more mass transferred, but I think it stays eccentric sort of as they go towards plunging together, which is, I think, at face value, really surprising. And what started me along this path was kind of looking at these amplitudes and saying, how can that be, basically? So, yeah.
Okay, were there any other questions in the audience or online? No? Here's your chance, Ramesh. One more question.
Shall I? Okay. This is what Josh was already asking, but from your simulations directly,
Yeah.
you already have some estimate of the orbital decay.
Yes.
At 11
Yes.
seconds.
Yes.
You also get a direct estimate of the eccentricity evolution.
Yes, you do. I think when I was looking at it, I think that is a little less well converged. So that's why I wasn't talking about that. So it's that interaction and those torques are there, but I don't actually believe them. Sorry.
And Pepe has a burning question.
Yes, Martin says I should ask my stupid question. So,
Burning
you've
question.
got strong shocks in this system,
Yeah.
right?
Yeah.
So, what about X-ray emission?
There doesn't seem to be any X-rays. So they did look at it. Jai Singh looked at it, and there's a relatively strong limit on X-ray emission. I think the only thing that can explain that to me is that actually the column is kind of large because of this kind of fluffy envelope. So presumably, if we went back in history 1,000 years ago, maybe there was a shock, but there was less mass involved, and that would be an X-ray emitting star. And then it becomes more and more mass rich, and it's coming out, it's reprocessed and coming out at lower temperatures. Qualitatively, sure, but like quantitatively, I don't know. Yeah. I mean, I think that's a beautiful point.
Okay, well, please join me in thanking Morgan again.
Thank you.
And thank you also again to Paul Hertelendy for the generous gift for this lecture. I think we're going to give you a nice one.
I love it.